Okay, good afternoon. The speaker of today is Maccary, who got a master from the École Normale Supérieure in Paris, and he also did an internship at the University of Ferrara. Now he's a PhD there, working under the supervision of Cristiano Guidorti, and he's working on the study of gamma-ray burst using data from most satellites. And today he's going to present the studies about that, also connected to the very hot topic of self-organized criticality. Please.
Hello everyone. So yes, I'm Maccary. As Franco said, I'm a PhD student at the University of Ferrara, and today I will talk about how self-organized criticality can help us to understand the bursty emission from gamma-ray burst. So gamma-ray burst.
You can click.
Yes.
Okay, yes.
Gamma-ray bursts are short-lived, bright gamma-ray flashes. They are the most powerful explosion that can occur on a stellar scale, and the amount of energy that can be released by such events can be comparable to consuming a solar mass in just a few seconds. As of today, we know two kind of progenitors are known to produce such objects, depending on their duration. It could be either due to the collapse of some kind of massive star, so-called collapsar, or it could be due to the merger of two compact objects, either to neutron star or a black hole with a neutron star. The object that is ultimately produced could be either a stellar mass black hole surrounded by a thick accretion disk, or it could be a highly spinning neutron star surrounded by a huge magnetic field, the so-called millisecond magnetar. In any case, a relativistic jet is produced, and as it propagates, it will convert parts of its energy into gamma-ray radiation, and this radiation is by some internal dissipation mechanism, and this radiation is what we call a gamma-ray burst. So from a time series point of view, gamma-ray burst is an incredibly complicated signal. It's non-stationary, it's transient, and its shape is completely unpredictable. So a gamma-ray burst could be just as well made of one pulse or few pulses, or it could be also made of several tens of pulses that are sometimes overlapping. And so one important question is, where does this diversity come from, and what this diversity is telling us about the inherent gene activity and about the dissipation mechanism. So gamma-ray bursts present flux variation on different time scales, and if ranging from 10 of seconds to a few milliseconds for the most variable ones. And if one wants to study how the power is distributed among these time scales, one can compute the so-called Fourier transform of the signal, and then the power density spectrum, or in short, PDS. And so gamma-ray burst PDS were studied either on individual gamma-ray burst time profile or in average ensemble of different gamma-ray burst time profiles. And it has been shown that usually the gamma-ray burst PDS decay with frequency according to a power law or a broken power law, with an index of that is typically ranging between 1 and 3. And as we will see, such PDS are also observed in totally different contexts, as we will see in a few slides. So a gamma-ray burst does not generally produce a steady emission of radiation, but is rather made of intermittent episodes of intense activity that are separated by episodes of inactivity. And if one wants to study this intermittency, one can compute the so-called waiting time, which is the time elapsed in between two successive events. And so waiting times observed during prompt emission, but also during the later observed X-ray flare were computed, and it has been shown that they are distributed according to a power law distribution with an exponent that is near to the value of 2. And we observe such power law waiting time distribution. We also observe this type of distribution in other astrophysical phenomena, as for instance, solar flares, as we also see in a few moments. So the hypothesis that the diversity of gamma-ray burst could be just due to different, could be just the result of different random realization of a common stochastic process that is working near to a critical regime has been put forward by two scientists that are named Stern and Venson in 1996. And in their paper, they made a model, a stochastic process that is called the stochastic pulse avalanche model that is able to reproduce, that is able to simulate gamma-ray burst-like curves. And this model had been recently optimized. The parameter of this model had been optimized by using a genetic algorithm. And this model is now able to very accurately reproduce gamma-ray burst diversity. So what is self-organized criticality? So self-organized criticality is a model that was introduced in the early 80s to explain by which mechanism some dynamical system can present a power density spectrum as the one that we saw earlier. So systems governed by self-organized criticality share a lot of similarities with gamma-ray burst. So firstly, they have this system often present a power density spectrum as for gamma-ray burst. We also observe a power law distribution of waiting times. And finally, in this system, we often see an avalanche mechanism when the energy is dissipated. The energy is dissipated according to a cascade or an avalanche mechanism. So self-organized criticality was initially illustrated with the example of a sand pile onto which some sand grains are dropped onto the top of the sand pile. And as these sand grains are dropped, the sand pile slope will become steeper, and until eventually it will reach a threshold above which the mechanical equilibrium cannot be sustained anymore. And above this threshold, the system will avalanches will occur to restore the lost equilibrium. And then, as other sand grains are dropped, the process will repeat, and the system will always stay close to this critical point and will release energy whenever the critical threshold is exceeded by the system. So self-organized criticality is made of two fundamental concepts, self-organization and criticality. So self-organization means that the system is not controlled by some external parameter, like, for example, the temperature in some phase transition, but rather evolves freely towards a more organized state. And criticality means that the system will oscillate in between an unstable and a stable state, and it will release energy whenever it will release energy in form of avalanches whenever this instability threshold is exceeded. And it's important to note that the avalanche size distributions are described by power law functions. So it's indeed a key feature of self-organized criticality, the single shots that occur in the avalanches are power law distributed. I mean, their properties are power law distributed. So the duration of one avalanche or the energy released during one avalanche are power law distributed. And in the simplest version of self-organized criticality theory, the power law distribution exponents only depend on one parameter, which is the dimension of, which is often called S, and which is the dimension of the space in which the energy is released. So, for example, if this parameter S is equal to 1, it means that the energy is released only in one direction. Then if S is equal to 2, it will be released in a plane. And finally, if S is equal to 3, it's released in a volume. The energy is released in a volume. So self-organized criticality has already achieved significant successes in astrophysics, being invoked in a wide range of astrophysical phenomena, starting from local events inside our solar system, like lunar craters or the shape of Hadron's ring, or even solar flares, to extragalactic events like flares from magnetars or for blazars, and more recently, gamma-ray burst. So in the case of solar flares, the accumulated statistics is excellent, and the experimental results are in very good agreement with self-organized criticality prediction. For gamma ray burst, instead, self-organized criticality enters in this field more recently with the study of the so-called X-ray flares. And also in this case, data and prediction of the shock theory could be in agreement, provided that the S parameter is equal to 1, which is slightly different from solar flare, where the S parameter is equal to 3. And instead, for gamma ray burst prompt emission, data and experimental results and prediction of the shock theory could be in agreement, provided that the S parameter is equal to 3, which is just like the case of solar flares. So the question is gamma ray burst prompt emission compatible with self-organized criticality? So I just said that there was some work that investigated the presence of self-organized criticality in gamma ray burst prompt emission, but especially in these studies lack two things. They lack first, they lack a gamma sample with accurate redshift measurements, and most of all, they lack an assessment of the impact of the selection effect. So in our study, we use a gamma ray burst sample with reliable, that means spectroscopic redshift measurement, and we carried out simulation of the impact of the selection effects. So for that matter, we used gamma ray burst detected by the Gamma-ray Burst Monitor on board of the Fermi Space Telescope. So the Fermi Space Telescope was launched in 2008, and it's made of two main instruments: the Large Area Telescope, which is a pair production telescope that is sensitive to very high energies, and the Gamma-ray Burst Monitor, which is sensitive to soft gamma ray radiations. And so the Gamma-ray Burst Monitor, it's an all sky monitor, so it's able to see the whole sky that is not occulted by the Earth. It's constituted of 12 NII detectors that are sensitive to soft gamma ray radiation, so from 8 to 1000 keV, plus two BGO detectors that are sensitive to higher energy, so from 200 keV to 40 MeV. So in our analysis, we started by subtracting the background. So we used the standard procedure of selecting so we used a gamma ray burst sample made of type 2 gamma ray bursts, so gamma ray bursts that are originating from a collapsar, to ensure that they were that these gamma ray bursts are originate from a collapsar. We selected long duration gamma ray burst, and we have excluded the non-cases of long duration gamma ray burst, long duration merger candidates, as for example 21, 12, 11A, or even also 23, 03, 07A. And we used gamma ray burst for which we have an associated spectroscopic redshift measurement. So in our analysis, the first thing that we did is to subtract the background. So we have used a standard procedure of selecting two temporal intervals, one before the burst and one after the burst, and we have interpolated the background in between during the gamma burst interval, and we ensure that the background was properly interpolated by looking at the residual distribution. After having subtracted the background, we have identified the pulses inside our gamma burst. For that matter, we use a peak detection algorithm called MEPSA, which is able to identify peaks in a noisy light curve. And MEPSA essentially scans the light curve at different time resolution, looking for excess applying a series of excess patterns to it to find different peaks in the light curve. So after having identified all these pulses, we modeled these pulses by using some pulse models. So we choose the Norris pulse model, which is made of 5 parameters. So the first three parameters are T0, which describes the pulse maximum time, A that describes pulse maximum rate, and tau R that describes the rise time of the pulse. And the two other parameters describe the shape. So nu the new parameter describes the shape of the pulse, and it's intermediate between an exponential function if nu equal to 1 or a Gaussian function if nu equal to 2. And finally, the C parameters rules ratio between the decay and the rise time, and it typically ranges from 2 to 4. So we model a whole gamma-ray burst by a superposition of all these pulses, and to compute the counts, so the integral inside of a pulse, we integrated over time the pulse model. So how to compute the energy that is released by each pulse? So it's the aim of analysis to obtain the energy distribution carried out by each pulse. So to compute the energy, we have computed the counts inside a given pulse by integrating the pulse model. And then we have computed the so-called conversion factor that is defined by the ratio of the total fluence integrated on the whole duration of the gamma-ray burst divided by the corresponding counts integrated on the exact temporal duration. And by multiplying these two quantities together, we obtain the fluence inside a given pulse. And finally, to obtain the energy, we multiply the fluence by a factor that is accounting for the gamma-ray burst distance. So we obtained the distribution of the energy emitted by each pulse, and then we try to model this distribution. So we consider two models, principally the Power law model and the Broca-Power law model, and we quickly realized that Broca-Power law model is preferred. So we clearly see a break in our distribution, but we ask ourselves, why is it so? Is it only due to experimental selection effects, or is it due to more fundamental reasons? So to answer this question, we had to understand selection effects and to model them. So the farther away you go into the universe, the farther away you look into the universe, the brighter a given gamma-ray burst has to be detected by some instrument. So this means that the faintest events cannot be seen at large distances. So this effect is often referred to as selection effect, or is also sometimes called a Malmquist bias. And so if you consider a population of gamma-ray bursts that are spanning a very huge distance, a very huge range of distances, it means that at large distances, only the brightest events can be seen. And so it means that the observed energy distribution, the distribution that you get from observation, is not accurately accounting for the true way the energy is distributed among these bursts. So a possible strategy to tackle this problem is to divide the sample into bins of redshift and to account for the different detection efficiencies for different bins of redshift. So the first thing to model the selection effect is to compute the detection efficiency, first as a function of pulse counts, and then as a function of energy. So we started by computing the detection efficiency as a function of the pulse counts. So to do that, we have simulated a given pulse, so a given gamma-ray burst, simulated with some noise and with a given number of counts. And by counting the amount of time this pulse was detected by your peak detection algorithm, we were able to compute the detection efficiency as a function of the pulse counts. And secondly, we have translated this detection efficiency as a function of counts into a detection efficiency as a function of energy by using the classical relation between the energy and the counts once the distance of the gamma-ray burst is known. So we have used for one given bin of redshift, we have used the distances of the gamma-ray burst inside this bin, and then we have averaged all these individual detection efficiencies to obtain one average detection efficiency for that bin of redshift. So once we have computed the detection efficiency in function of the energy for a given bin of redshift, we are now able to simulate the detection process and so the selection effects. So we started by simulated a theoretical shape of the energy distribution. So we assumed that the true energy distribution is maybe given by a Power law. So the blue points in this plot are drawn from a power law probability density function. And then as we are able to compute the detection efficiency, we have simulated the detection process by performing Bernoulli trials. So these Bernoulli trials consist into selecting a given pulse of energy E and computing its detection efficiency, and then draw a random number in between 0 and 1 uniformly distributed. And then if this random number is lower than the probability, the detection efficiency, then the point is considered to be detected, and otherwise it's not detected. And by performing these trials on all the points inside the blue distribution, we get the orange distribution, which is the distribution of detected pulses. And as you can see, the selection effects are the difference between the blue and the orange distribution, and they become more and more important as we go to lower energy values. Okay. So we then have replicated our analysis to all the bins of redshift present in our sample, and finally we have merged these results all together to obtain the distribution of detected pulses that we can now compare to the observed distribution. So here we have, again, we have simulated, we have assumed some shape for the energy distribution. This time it's given by a broken power law. And then we have applied the detection process to obtain the detected pulses. And now we are able to compare this distribution with the observed one, and we are able to find the best parameters that give the best fit of our data. And as you can see, even after having accounted for selection effects, a broken power law model still gives a better description of the data than a simple power law. So here are results. So here are shown the 4 distributions that we have considered. So energy, luminosity, duration, and waiting time. And we have modeled this distribution by power laws plus either a break or a flattening at low values. And here you can see the power law distribution exponents for the 4 distributions that we have considered. On the top, you can see the best fit associated with the error bars. And on the bottom panel, you can see how our values compare to other values available in the literature. And the dashed and the dotted line represent the prediction of self-organized criticality for S equal to 3 and S equal to 1. And as you can see, we globally, overall, our results are compatible with self-organized criticality, even if we observe some deviation, especially the fact that we observe broken power laws instead of simple power laws. So while self-organized criticality is useful to describe the data, yet it does not provide much physical insights. However, some physical phenomena can result in self-organized criticality, as for example, turbulence and magnetic reconnection. So turbulence manifests as chaotic random flows, where eddies of various scales can form, and the observed energy spectrum is a power law in some range. And magnetic reconnection, instead, it's a way to convert the energy stored in some magnetized plasma into radiation, into heat accelerated particle that will radiate afterwards. And while the simplest model of magnetic reconnection predicts much lower reconnection rate as the one observing in astrophysics, turbulence may enhance the reconnection rates, making magnetic reconnection a credible scenario for emission of radiation from relativistic jets. So indeed, turbulence can make magnetic reconnection at very small scales, accelerating and triggering an avalanche of magnetic reconnection events. So the last question is there a model of gamma-ray burst emission that produces avalanches similar as the ones observed in self-organized criticality? So this is an open question, but there are some already existing models that can provide the beginning of an answer. One of them is the ICMARC model, in which 2 mildly magnetized shells will collide and shock, disrupting the initially ordered magnetic field lines, and then the turbulence regime will set in and will further distort these lines, and until these lines become so distorted that the condition for fast magnetic reconnection is reached. And after above this threshold, a cascade or an avalanche of magnetic reconnection events will happen and produce the gamma-ray burst. As you can see, this model shares a lot of similarities with self-organized criticality and contains also key ingredients of it. So to conclude, self-organized criticality is a model that can be used to describe the dynamics of some dynamical system. And our paper in our paper, we have investigated the presence of self-organized criticality in gamma-ray burst, and our paper is the first that takes into account the selection effects. And so our results are globally compatible with self-organized criticality with a dimension of S equal to 3. But even if we observe some deviation, especially the presence of breaks inside our distributions. And finally, we saw that some theoretical gamma-ray burst emission model already contains some elements of self-organized criticality. Okay. Thank you for your attention. You can find our paper by looking at this. Thank you.
Questions for the speaker? Yeah.
When you consider waiting times, what happens if you miss a peak? I mean, that is possible when it is going up, for example, because like that.
Yes.
Is it critical? Does it change very much?
We can miss a peak. Most of all, if there are two peaks that are closely tied together, so they are not well separated, then the efficiency of our detection algorithm will drop. So it could be important, for example, at low values of the waiting times. That's why you can see that in our distribution, this one, we did not consider the first bin because this effect will be very important at low waiting times because the two peaks will be badly separated, and so our detection algorithm can see one peak instead of two. So yes, this effect could be important, and we have to take it into account.
Second question.
Yeah.
Sorry. When you are considering how many bars you take by Redshift and how many you're missing, there must be some assumptions on the ones you are missing. For example, that they are always of the same kind or something like that.
Do you mean when we are considering different bins of Redshift?
When you compute the number of detected with respect to the number or the total number.
Yes.
At that Redshift range, you assume that they are always the same, something like that.
The number of detected
Yes.
per bins of Redshift. Yeah, we try to take the same, approximately the same number inside to have the same situation. I'm not sure. So,
you must assume that you know something about the ones that are not detected. They are like the ones that you detected or something like that.
I mean, we chose to.
We can talk about that later.
Okay, I want to understand better something. So I understand the analogy with supercriticality. As I was telling you before, if people don't know, it's super cool. I mean, it's one of the possible models in which people are also trying to explain higher order function in the brain, like complex system organizing altogether on large scale. In the case of gamma-ray burst, I don't understand what it would be the equivalent of the critical angle in the sun pile model. So what is the
in gamma-ray burst?
Yeah, what is the quantity or combination of quantities that would lead you into criticality?
So in the Ekmark model that I've talked about here, so there is some instability threshold. It's difficult to know exactly which instability is triggering the gamma-ray burst. But we know that, so initially you start with ordered magnetic field lines. And so the first shock will disrupt a bit this line, so they will be a bit distorted. Then you have turbulence that sets in, and it further distorts these lines. At some point, the length of the wandering is called the wandering length. So it's the length on which, after which the magnetic field will change its direction, becomes so small that this condition for fast magnetic reconnection is reached. So it will be a condition on the length, on the wandering length of the magnetic field. But I think I am. Yeah, it's this quantity that you can find it also here.
So those are, I mean, in turbulence, you have like, the criticality would be, for example, if the Reynolds numbers or magnetic Reynolds numbers is larger than blah, you undergo the turbulent regime. Okay. This looks like the combination of all these processes.
Yeah, it's a combination of shocks and turbulence. And turbulence will help to distort the lines. And at some point, it will be so, the line will be so distorted that this kind of reconnection, fast reconnection can happen.
Okay. But the energy slope that you have, I don't know, in classical chromogoral turbulence has a different spectral shape, is -5/3, etc.
Yeah.
So all of these still can be compatible with the spectra you're measuring.
Yeah, I mean, we observe also power laws in turbulence.
Yeah, but with a different slope usually.
Yeah. I don't know if these slopes are related in some way to self-organized criticality. It's not so obvious
Okay.
to know if it's related.
And direct simulations of this, like fluid dynamical simulation of these are.
There are some simulation of relativistic turbulence where we are trying to see if the rate is compatible with what we observe in relativistic plasma.
Okay. Any other questions? Not from.
Yeah. The fitting of the energy distribution. Yeah, if I understand correctly, you feed the data and then you keep the distance.
Yeah.
Have you tried different techniques like fitting the events one by one according to their energy with a probability distribution? So in a
we fitted being data. But we tried different functions like t-squared or different optimizers.
With the fit of the events one by one, considering also the uncertainty of the energy, maybe can show some variations in the final slope. So sometimes if you are being independent, varying the number of beams can also maybe change the results. And we also try different beams.
So binning, we try to ensure a minimal number of events inside the beam. So I think we choose at least 10 events per beam to ensure statistical quality.
Okay, I don't see question from Bob, so okay, it's the end. Thanks.